So we know what a Markov process is and a transition matrix is. And now what we're going to take a look at are regular stochastic matrices. A stochastic matrix is a square matrix, so same number of rows as column, like a 2 by 2 or 3 by 3. So it's a square matrix in which all the entries are non-negative, so no negative numbers. Non-negative means 0 or positive, in which all the entries are 0 or positive numbers, and all the entries in each column add up to 1. Now, here is an example. So we had this one, the working women, not working women, working, not working. So our transition matrix that we looked at in the last section was this one, 0.80, 0.20, 0.30, 0.70. And you can probably see that this is stochastic because look at all the entries. They're non-negative, right? No negative numbers. And if you add the numbers in the columns, you get 1. So this matrix T, this is stochastic. Now here's a particular type of stochastic matrix. This one is called a regular stochastic matrix. And a regular stochastic matrix is just a stochastic matrix, right? A square matrix in which all the entries are 0 or positive numbers. But a regular stochastic matrix has this property. You take some power of your matrix and it eliminates all the zeros. So for some power of that matrix, all the entries are positive numbers. Here are a couple of examples. If we have this one right here, right, that 0.80, 0.20, 0.30, 0.70, this is regular. Do you see why? It's regular because, okay, it's stochastic first of all, but all the entries are positive numbers. There's no zeros here, and that makes it regular. Now this matrix here, T equals, all right, it's still going to stick with the 2 by 2. Let's do this one. Let's do 0.8 and a 0, and then a 0.2 and a 1. Now this is not regular yet. We don't know that yet because there's a 0 here. But what we need is, if we can eliminate that 0 for some power of T, then it's going to be regular. So let's square this, see what happens. Now, I squared this on my calculator, and when I squared it, here's what I'm getting. I am getting 0.64 and 0.36, and I'm getting a 0 and a 1 right back there again. So I can't conclude yet that it's not stochastic regular because maybe I need to take it to the third power. And if I took it to the third power, that 0 would disappear. Let's try that, see what we get. So if I take T and cube it now, here's what I came up with. I got 0.512, 0.488, and then I got a 0 and a 1. There's that 0 again. So I'm going to make a statement here. I'm not going to prove it, but we could prove this. I'm going to say this. If a 0 occurs in the same position in 2 successive powers of the matrix, then it will appear in that position in all higher powers of the matrix. So look what we have here. I've got a first power, I got a 0 here. In the second power, I've got a 0 in the same position. In the third power, I've got a 0 in the same position. So I'm getting a 0 in the same position in 2 successive powers. So no matter what power we raise this to, we're going to get a 0 there. And hence, if I get a 0, this matrix back over here is not regular, right? So we conclude that this matrix is not regular. Now here's what I'm going to do. Another example, I'm just going to switch that 0 and the 1 from the last example. So I'm going to put the 1 on top in first position, the 0 in the second. And when we compute this one, let's compute T squared. It's going to be 0.8, 1, 0.2, 0. I'm going to square that, and I'll do that on my calculator. When I squared that, I got 0.84 and 0.16 on the first column. Those numbers add to 1, right? And then 0.8, 0.2. So what I've got now is I've eliminated all the zeros. So what do I know about this one up here? That is a regular stochastic matrix. One of the many applications of Markov processes or Markov chains is in making long-term predictions. So we're going to say this now. If the transition matrix to a Markov process is regular, All right, so if it's regular, then the Markov process reaches a steady state. Now, what does a steady state mean? That means the next generation is not going to change from the current generation, right? Things tend to settle down, and in the long run, one generation is the same as the next.